So I'm giving you the review sheet early just so that you have some time to work on it this weekend if you get around to it or have time to. I am still giving you Monday to work on it, and we'll go over it Tuesday. Okay? So I know sometimes Monday, the one day in class is not always enough for some of these review sheets to get it all done in class. So I'm giving you a little bit extra time so that you can work on it and get it done. And then Tuesday we'll go over it, and Wednesday is your test. If it ends up, we'll see how it goes. And if you do need an extra day, that is fine. I will give you kind of a day or 2 days. We'll see how it goes to get it done. And then we're going to be moving on to chapters 5 and 6. Now, a lot of stuff in chapters 5 and 6 are actually not that bad. We're going to go back to systems of equations, graphing, matrices. There's going to be one or two things that is new for some of y'all not so much. So that's looking ahead. Now, the first thing we're going to look at is this here. Now, solving an equation for a special variable. Literal equations is what we call these also, literal equations. You did these in Algebra 1. We did them, I don't think we covered them in Algebra 2 much at all, because there's not a whole lot to them. So for the first one here, given P is equal to 100 e to the kx minus 100, solve for x. All we're doing for this here is getting the variable by itself. We're just solving for that one variable in particular. And in this case, we're wanting to get the x by itself. Well, to do that, the first thing we can do is add 100 to both sides, which will tell me that P plus 100 is equal to 100 e to the k times x. So it's very similar to what we've been doing with solving, what we did the other day with solving these here for x or the variable. But in the end, we're not going to have a specific number. Now, the next thing we can do is divide both sides by 100, telling us that e to the kx is equal to p plus 100 over 100. Any questions on this so far? Well, the next thing we need to do is to get rid of the e and specifically get x out of the exponent. Well, the only way to do that is to apply a logarithm to both sides. And in this case, we're going to apply the natural log. And whenever we apply the natural log to both sides, one of our properties of logarithms is that we can move the exponent out front, which does give us k times x. And the natural log of e is 1. So it tells us that k times x is equal to the natural log of p plus 100 divided by 100. Now at this point here, x is almost by itself. The only thing we have left is to divide both sides by k, telling us x is equal to the natural log of p plus 100 divided by 100, all divided by k. And it's not that we're actually solving for anything, we're just trying to get the one variable by itself using the operations that we've had in order to do that. Any questions on this here? well, I'm not going to focus so much on the other one, but that's all we would need to do for that there. Now what we're going to spend the rest of the time today with is solving these quote-unquote real-world problems, using the properties of logarithms to solve these here. Now the first one is, suppose that $15,000 is invested at the end of 3 years. The value of the account is $19,356.92. Use the model A equals PE to the RT to determine the average rate of return R under continuous compounding. Well, this here is our starting equation. Our principal is what we start with. 15,000 E. Our rate is what we're trying to determine. So it's going to be R. But the number of years, our time, is given to us as 3. So if we're looking at the starting equation, A is equal to 15,000 E to the RT. E to the R times 3, or 3R. This would be our starting equation, what we're starting with. Now to solve this, what we're going to do is we're going to replace the A with our amount, $19,356.62. Now I did rewrite R times 3 as 3R because that's more natural as we would actually write it. We wouldn't keep writing R parentheses 3 close parentheses. It is still the same as 3R. Now at this point here, we just need to get the R by itself. Now the first thing to do is we need to get E, our exponent here, by itself. And to do that, we're going to divide both sides by 15,000. Now here, 15,000 divided by 15,000 is 1, leaving us with E to the 3R. Now the question is, and I believe I know the answer to this, 19,356.62 356.62 over. Okay, thank you. Just 92. Thank you. It's amazing how much I work with numbers, but I cannot keep 4 digits straight going from one screen to the other. Now, the question is here, will this give us a nice number? Well, no. We could try to turn it to a or back to a fraction, and no. And so what that means is that we're going to have to leave it as our fraction. We're going to have to leave it as 19,356.6. Thank you. That's where 92 over 15,000. We'll have to leave it as this here. Now, for some of the problems, it might work out nice. Because if we had, say, instead of $19,356.92, it somehow miraculously worked out to be exactly 20,000, then we can simplify it. Because 20,000 over 15,000 is a nice 4/3. If the number reduces to a nice number or a nice fraction, we can reduce it. If it doesn't, we're kind of stuck. Now, the next thing we can do is to get rid of the E. Well, the only way to get rid of the E is to apply an ln. Because ln of E to the 3R comes to the front, and ln of E is 1, leaving us with 3R. The other side, we have the natural log of 19,356.92 over 15,000. Well, if we know that our number inside the natural log is not going to be nice, we know for certain the natural log of that number is definitely not going to be a nice number. So what we can do is finish this out by dividing both sides by 3, telling us r is equal to the natural log of $19,356.92 over 15,000, all being divided by 3. So we start off with a fraction, ln fraction $19,356.92. I got that right, yes? Over 15,000, all divided by 3. .08499. And if we look back here, determine the average interest rate, 0.084999. Or normally, and especially if you're actually looking at actual interest rates, they really don't go past the 100th place. So what we could say this is actually is 0.085. Now, for your actual answer, they're going to want this as a percentage because we're talking about an interest rate. Interest rates are always given in percentages. So our rate is actually going to be 8.5%. So the answer we would give is 8.5%. And that's kind of why we don't go past the thousandths place, our third decimal place. Because most interest rates are given as this here. We don't go normally one decimal place, more than one decimal place after in the percentage. And if you can actually find a savings account or a money market account that's actually 8.5% for most of the basic rates, that's actually really good. Some of the best CDs and stuff right now are going at about 4 or 5. And then they jump at about 100, okay? Yeah, it's a little crazy. But questions on this here. On January 1st, 2000, the population of California was approximately 34 million. On January 1st, 2010, the population was 37.3 million. Write a function p of t equals p naught e to the kt to represent the population of California, p of t, in millions. T years after January 1st, 2020. Round k to 5 decimal places. So, the first thing we want to do is figure out what k is. K, our percent of increase, rate of increase. To do that, we're going to use this formula. P sub t equals p naught e to the kt. Well, p naught is going to be our original, our starting value. And our starting value is 34 million. But to keep everything in simpler terms, we're just going to state it as 34. E. We don't know what k is, but how much time has passed for what we want to set it equal to? From 2000 to 2010, 10 years have passed. And our P of t, what it's equal to now is 37.3 million. So all we've done so far is just plug in the information that we know. So we're looking really at P of 10 years. So our t value on the right-hand side is 10. P of t we already know. P of 10 we already know is 37.3 million. So we have everything set up because if whatever value k is, when we plug it in here, will give us 37.3. We just need to solve for it. So we're going to do the exact same thing we did on the last problem. So the first thing we're going to do is divide both sides by 34. These will simplify, leaving me e to the 10k is equal to 37.3 over 34. Now, I have a feeling you can probably guess that 37.3 divided by 34 is not going to be a nice number no matter how we slice it. So we can leave it as that there. The next thing we need to do is simplify e. So we're going to take the natural log of both sides. The left-hand side will have ln of 37.3 over 34 is equal to, well, the 10k comes to the front and out of the exponent. And ln of e is 1. And the last thing we need to do is divide both sides by 10, telling us that k is equal to the natural log of 37.3 divided by 34 all over 10. 34. ln of 37.3 over 34 divided by 10. 0.009. 0.00926 is our decimal here. Now, round your answer to 5 decimal places. And it would actually indeed be 0.00926. It would round down to this here. So this here is our k value. Any questions on how we found the value of k for part A? We're ready for part B. Part B. Use the function in part A to predict the population on January 1st, 2018. Round to 1 decimal place. So we're going back to P sub t is equal to 34e to the 0.00926 t. This is the equation we got from our equation in part A. Now what we're trying to find is January 1st, 2018. Well, we're not taking it just from 20,000. We're not going to plug 2018 in there. We're just going to plug in 18 because we're talking about years since 2000. And 2018 has been 18 years since 2000. So our time t is 18. So we have 34e to the 0.00926 times 18. Now at this point here, this is even easier than what we did earlier. 926. Because at this point here, we can just type the function in. Hit enter into the nearest 1 decimal place. So 40.16, which is going to be 40.2. Any questions on part B? Kind of part B was nicer than part A. We didn't have to do a whole lot besides sticking the numbers into the formula and calculating it out. Now the last part, part C, use the function from part A to determine the number of years during which the population of California will be twice the value from 2000. So twice the value. Well, if it started out at 34, twice the value would be what? 78, yes? No. Not 78, it would be 68. For some reason, I wanted to carry a 1 over, but 68. And what's interesting with this here, and especially these twice, double or triple the value, whenever we get the E term by itself, we end up getting 2 is equal to E to whatever the exponent is. If it asks for us to triple it, what is triple? How long will it take to triple the population? We'd essentially get to the same spot, but instead of having 2, we would have 3. Or 4, or whatever the amount we're wanting to increase by. Now the next thing we can do is take ln of both sides, like we did with the first part. On the left-hand side, we'll have ln of 2. On the right-hand side, the 0.00926 t will come to the front, and again, ln of e is 1. And last but not least, we're going to divide both sides by 0.00926 to get those to simplify and leave t by itself. And in the calculator, fraction ln of 2 divided by 0.00926. Let's see what it asks for our number of decimal places. Write a function determine the year during which the population will be twice. So that would be 74 point, I know I just looked at it, 85. And this is years since 2000, yes? So if we add that to it, we'd have 2074.85, yes? Now, if you did put the 0.85 in, it would count it wrong. And it's all in the wording. Because I'm going to look at the wording one last time. Because use the function to determine the year during which the population will be twice the amount, yes? So if we're talking about 0.85 years, we're still in the middle of 2074, yes? So the year in which the population would have doubled is just 2074. We don't have to put the decimal because we're still in the middle of the year. And most likely we're going to be somewhere in November, if I would take a guess. Nope. Actually, September, October. September, 10th month. October, yep. If only they kept the months matching up with their numbers, it'd be nice, wouldn't it? But any questions on this here? Most of this is not too bad. Now this one here and the next one, I put these in here intentionally because how we write this out is a little weird. Because what they want us to do is use this here, the population P of T of a culture of bacteria is given by the equation. P of t is equal to 5,000 times 2 to the t over 4, where t is the time in hours after the culture was started. Write the rule of this function using base e. So we're wanting to rewrite it with base e. Now, rewriting it with base e, we will still have the number in front. We'll still have the number in front of whatever number we're having to the exponent. So here, the number is 2. So the number 5,000 in front will still be part of our answer. This is where this comes into play. B of t, b to the t, is equivalent to e to the ln of b t, b times t, ln of b times t. So what we're saying for this here is 2 to the t over 4 is equal to, or we can change it to e to the natural log. Well, our b value in this case is 2, and our t, the exponent, is this here. So we'll be multiplying this by t over 4. So what we're saying is 2 to the t over 4 is equal to e to the ln of 2 times t over 4. Or as we can put this in here, e to the ln of 2 divided by 4 times t. And that's part A. Any questions on part A, writing it in E form? Okay. Find the population after 12 hours using both formulas from part A. So P of 12. So we'll start off with the one we found. 5,000 E to the ln of 2 over 4 times 12. E to the ln of 2 over 4 times 12 is, interestingly enough, 40,000. I kind of like how that works, but now they also wanted us to use our 2 to the p over 4, our original formula. It's the exact same amount. I think that's kind of frustrating to find a formula that does not give us any more accuracy or change anything about the actual values. It gives us the exact same thing. Questions on any of this here? I want to look at one more of these here, doing this. And the biggest thing I would say with these here is first write the formula. So if this is going to be one of the homework assignment type problems that you'll have. A sample of radioactive substance has an initial mass of 22.7 milligrams. The substance follows a continuous exponential decay model and has a half-life of 7 hours. Now, when we talk about half-life, So we'll just say y just to keep with, especially how part A has the equation written y equals. We'll keep them the same. We always start off with our initial amount. The initial amount that we have times here, half-life is understood to be 1/2. That's part of the reason why we get the term half-life. 1/2. To the t for time divided by whatever unit they give us. So they told us 7 hours, so we're going to do t over 7. So for most of these here, I would start out with the original problem, and especially with this one here with half-life. So we'll have our initial starting amount times 1/2 to the time divided by whatever the time they gave us of the half-life amount. Now to write it in our E form, we will still have the 22.7. E. In the exponent of E, we're going to take the natural log of whatever our base was. So in this case, it's going to be 1/2. And it's going to be multiplied by t over 7. And that there is the equation. Now, if you notice in the answer choice, or the answers that they gave you, we had 2 spots to plug stuff in. One of them is going to be our 22.7. So the 22.7 will go in front of E. Now, if you notice, there's another spot, and the t is by itself. So we can't just plug it in as the natural log of 1/2 times t over 7. So all that means is that what we're actually plugging in is the natural log of 1/2 divided by t, or not t, 1/2 divided by 7 times t. So this first part is 22.7. The other part is going to be the natural log of 1/2 divided by 7. So do we kind of see how this works out? And again, I wanted to do this with y'all because this one here can be a little bit confusing on what we're doing for the first part. The second part will be present after 18 hours. We just plug 18 in for t. So 22.7 e to the ln of 1/2 divided by 7 times 18. Do we think, or do we expect this number to be bigger or smaller than our starting amount of 22.7? Because we're talking about half-life. Half should be getting smaller. 3.818. Nearest tenth, 3.8. 8 ones, so it'd be 3.8. Because I think I've talked about this before, but half-life is the amount, so each half is the amount of time for it to decrease by half of its amount. Questions on this here? So with this half-life and decreasing its mass, will the mass ever get to 0? If I keep taking half, will I ever get to 0? No, we'll get close to it because I can keep splitting something in half, but it'll never eventually reach 0. Any questions on any of this here? We feel good with most of this? Because I think we do have, this is the last one, so we'll finish up with this here. In most of the assignment, there's one problem like the one we just did. There's only one of them. But the rest of them are going to be like the first few that we did and this one here. they will give you the equation. They will give you the starting equation. So here, they gave us QT equals Q naught E to the negative KT, where QT is QT of carbon 14 remaining after T years if no additional carbon is ingested. I'm about to say inserted. Wrong word. So, write a model for this here. So carbon's half-life of this. So, represent Q of T. Carbon 14 remaining after T years if no additional amount is inserted. What am I missing? So Q of T is equal to, or Q naught, why am I missing one piece? Represent T, E, well, that's not Q naught is the half-life of this amount. So our E is going to be negative T over our 57,030. And then I believe this is going to be Q naught because they didn't give us an official amount to start with. The moments when I wish I looked at this a moment ago. Chapter 4. Okay. This, I'm glad we went over this. E negative, it's actually going to be negative 5,730 T. Sorry, not T. Losing my mind. Okay. And because what we're saying is we want to find the specific values. We want to find the specific value of K. So we're saying, and this is finally starting to make sense, and I'll explain it here. Half-life signifies that something, here in this case carbon 14, after 5,730 years is half of its original amount. So if our original amount was 1, in 5,730 years, we are at half of the original amount. Whatever K, this rate of decrease is, after 5,730 years, we're at half. So Q0 was our starting amount. And after this amount of time has passed, we are now at half of whatever that amount is. Now we can divide Q naught from both sides. They're just going to cancel, telling us that 1/2 is equal to E at this point here. We're going to take the natural log of both sides. So the left-hand side is going to be the natural log of 1/2 is equal to negative 5,730 K. Natural log of 1/2 divided by negative 5,730 0.00012 is our value of K. So that tells us that our original equation, all the way back up here, Q sub T is equal to Q naught E to our negative 0.00012 T. In part B, we're going to set the 76.6% equal to, really is going to be our E T. Now, it seems like Q naught disappeared, and most likely it's going to seem that way because we're going to treat Q naught as one, or I think they have a better way of saying it. We have it on both sides, and it's going to simplify out. Now, we'll need this as a decimal. Now, at this point here, we would take the natural log of both sides, which will tell us that ln of 0.766 is equal to negative 0.00012 T. To get our answer. I would lose the number 766 divided by negative 0.00012 is 222,221 years. And that is it.